In recent years, e-commerce has exploded in growth. E-commerce is basically trading of goods and services on the internet in exchange for a monetary payment, and every such transaction is made possible by a payment system operating in the background. However, implementing a payment system is not a leisure task. Reliability and correctness are critical. Furthermore, successful businesses generate a lot of payment requests as they scale, since even a small amount of downtime could mean a lot of lost revenue. Availability is also essential. In this video, we're going to demystify the process of implementing a reliable and scalable payment system. Before diving into the interview questions, it's useful to have a high-level view on the payment systems used globally. Normally, a customer places an order to a merchant website. To complete this, the customer has to provide the payment informations. So, next, the merchant sends the customer to the payment form page to introduce the payment details. Normally, this form page is provided by the payment gateway. To operate legally, this service has to manage many compliance rules, including PCI DSS and GDPR. This gateway also has several other functions. For instance, it can forward the request to advanced verification services for risk and fraud prevention. We'll discuss it later in more details. So, the main function of the payment gateway is to validate financial credentials and transfer them to a merchant bank account. Now, the cardholder information are transmitted to the acquiring bank. This is the bank that processes card payments on behalf of the merchant. Now, we can define a payment service provider. This is a broader term for third-party companies that assist businesses in facilitating payments safely and securely. A PSP usually offers services such as risk management, reconciliation tools, and sometimes even services for order management. PSPs can also be the acquiring bank, but not necessarily. Next, the acquiring bank captures the transaction information, performs basic validation, and routes the request along the appropriate card networks to the cardholder issuing bank for approval. Finally, the customer bank receives the transaction information and responds by approving or declining the transaction. It can check that the transaction information is valid, the cardholder has sufficient balance to make the purchase, and the account is in good standing. And then, the transaction follows the same route back to the merchant. The merchant will receive a status of the transaction, which is also displayed to the client. First, we'll need to establish the requirements of the system and define what we want to achieve. In the beginning of an interview, it's critical to ask refining questions in order to clarify the functional needs, the scope of the system, and also the non-functional requirements. The first question to ask is, what kind of payment system are we building? There are basically two ways to do it. The most common use case is to build a payment system while using a PSP like Stripe or PayPal. This is normally used for online stores, SaaS platforms, or any other platform that requires payments. In simple terms, a PSP moves money from the buyer account to the merchant account. Then, the other way is to try to connect directly to banks or card schemes, such as Visa or MasterCard, without a PSP. However, these direct connections are uncommon and difficult to establish. To do that, we'll have to comply to the following standards and regulations. In general, these are required to make online transactions secure and protect users against identity theft. Getting all the compliance is not impossible, yet it's very complicated to achieve. And for every country, the process is a little bit different. So, most companies, even the large ones, make use of the payment gateways. Using a PSP also implies that we don't have to store card data in our system. That would be stored and processed by the PSP. This spares us from implementing extremely high security systems. Using a PSP makes the payment system a little bit easier, but we still need to take care of the logic to process transactions. First, a payment system interacts with a lot of internal services and external services. Second, when one of the services fails, we may see inconsistent states. Therefore, we need to plan for transaction failures and perform reconciliation to fix any inconsistencies. This leads us to the system requirements. A payment system is easy to understand at the functional level. It needs to move money from account A to account B. However, what's more difficult is to make the system reliable, especially when unknown situations are revealed. A small slip could potentially cause significant revenue loss, and there are a lot of things to consider when building a reliable payment system. In this video, we'll focus more on the technical concepts as they are applicable to almost every system. The business part will depend on each particular system. Also, we'll see how we can handle large throughput of payment requests. Let's say we need to build a payment system for an online store. Then, we should provide at least the following core features. First, when a user clicks the Place Order button, a payment event is generated and sent to the payment service. This service will coordinate the payment process. First, it stores the payment event in the database. Second, it will call an external PSP in order to process the card payment. When we call the PSP, we should provide at least the monetary amount and currency. Normally, this is captured from the checkout page. At this point, the user will see the payment page. This is where the payment details are collected. Usually, there are two ways to provide this page. We can use the form page provided by the PSP, or we can build it in-house. The second option is very uncommon and doesn't justify the effort. If we build a payment page ourselves, it means that we also have to store sensitive payment information. Again, this is a very tedious task. Normally, it doesn't make sense to go through the whole compliance process unless you're a large company who can justify such an investment. So, the common way of collecting and forwarding payment data is via a form page provided by the PSP. Then, the main function of the PSP is to send card details to banks or card schemes. After the PSP has successfully processed the payment, the coordinator service updates the wallet. In order to keep track of the account balance of the merchant, we use the concept of wallet. Then, the updated balance information of the wallet is also stored in the database. After the wallet service is successfully updated, the payment service updates the ledger. This involves logging all the financial transactions record by record. We use this service in post-payment analysis when calculating the total revenue of the e-commerce website or to support auditing. Finally, the ledger service appends the new information to a database. Internal and external services need to talk to each other to exchange information and get things done. There are two main communication patterns: synchronous and asynchronous. Communication is synchronous when one service sends a request to another service and waits for the response before proceeding further. In async communication, a service doesn't wait for the response. Instead, it continues with its own execution and it polls for the response at regular intervals of time or is notified about the response. What shall we choose for a payment system? As always, there is no straight answer. Before comparing the two patterns, we have to consider some facts. First, we have to consider that any of the involved services can fail at any time. Maybe one of the services stopped responding because of an intensive workload, or maybe some host servers have crashed. Second, let's consider the channel of communication. Almost all communication between services is done over the network. This channel can be slow mainly because of congestions, and it can also be unreliable. Requests could be lost on the network simply because someone unplugged a network cable. In general, many things could go wrong on the network. Considering these facts, we might realize that the sync connection is not really fitted for most cases. This is mainly because it's not tolerant to failure or big latencies, and because it doesn't isolate the failure, it will reduce the availability of the whole system. So, there's always a risk of cascading failure. If the PSP or any other service fail, the whole system is considered down and the client will no longer receive a response. The same cascading effect applies when one of the services is low. Here, the caller service is blocked until a response is received. So, if any of the services in the chain doesn't perform well, the whole system is impacted. These drawbacks are mainly a result of tight coupling between the services. We almost always want to avoid strong dependencies between components. This applies in programming and system design as well. However, in some use cases, we cannot proceed without a response from the upstream server. For instance, physical store payments require real-time authorization from the API. We should know immediately if it's a success or a failure. But we should use synchronous communication only if there is no other way. In most cases, we should prefer asynchronous communication because the services are loosely coupled. Particularly for a large-scale payment system with complex business logic and a large number of third-party dependencies, asynchronous communication is a better choice. Furthermore, asynchronous communication makes it easier to deal with uneven traffic and spikes. In these systems, we can make use of persistent queues such as Kafka that can act as buffers. If the service encounters a sudden increase in traffic, we store the requests and process them at constant pace without blasting the service with a lot of requests at once. We even have enough time to spin up some new servers in the background and then take the requests from the queue and process them at a faster pace. Moreover, according to its official website, Kafka is used by 7 out of 10 banks and financial companies worldwide. In conclusion, async messaging is suitable in most cases, for example, online payments, fraud detection, and analytics. This is because it's tolerant to failure and big latencies. In a payment system, we can encounter at least the following kinds of issues. System failures. Here we have the usual network and server failures, poison pill errors, when an inbound message cannot be processed or consumed, and functional bugs where there is no technical errors but the results are invalid. So, implementing a reliable payment system comes with a lot of challenges. The good news is that we have many tools at disposal to deal with the impediments. In payment systems, there are a lot of services involved that need to communicate with each other in order to complete a transaction. But how can we guarantee that any of the request messages doesn't get lost on the network? Or guarantee that a message is received considering that we may find unavailable services? To guarantee transaction completion, we can use a messaging queue like Apache Kafka. For any order placed or paid, we also create an event in Kafka. This component will help us persist communication messages so that they are not lost even when things don't go as planned. In this case, the payment operation doesn't complete successfully until the event is safely stored in the message queue. Now, we might consider that Kafka can also fail. However, since its job is so simple, at this point it's just to store messages, its availability is normally much higher than other business-related services. Then, these messages can be consumed individually by each interested service. Also, it's the responsibility of the consumer to mark the message as seen or consumed only when the message is successfully processed and stored in the database. In this way, once the sender successfully posts the message, it is always stored on disk on at least one data store. In addition, this is most probably also replicated. So, using this pattern, we can guarantee that messages will be delivered to the other services. Sometimes, in order to complete a transaction, we may need to get some information from other services. For instance, we may need to get the search results of a query. In those cases, it doesn't make sense to use a message queue. Still, payments requests may still fail because of network issues and other problems. So, to make sure that the request navigates safely on the network, we have to plan for the failure. Here we have some useful tools. For example, a customer may try to make a payment, but the request fails because the network connection is unstable. In those cases, it makes sense to retry the operation because network problems are usually temporary, and on the second or third attempt, the request might succeed. This is pretty straightforward to understand. However, we have to pay attention to the number of retries and the appropriate time intervals between the retries. Let's discuss the time intervals. Here, we may apply several strategies based on what failures we might encounter. The most basic retry implementation is to retry immediately after the failure. However, it's unlikely that the issue has been solved in such a short amount of time. Furthermore, it's important to give a little bit of break to the called service to recover if it was down. Otherwise, we can waste computing resources and also overload the system. So, we can retry at fixed intervals of times, or better yet, at incremental intervals of time. Now, the system has a little bit of break to recover. Still, a more advanced retry strategy is exponential backoff retry. Here, we double the waiting time between retries after each retry. So, usually, it is recommended to use something similar to the exponential backoff algorithm. This way, we can ensure that clients aren't hammering an overloaded server and contributing more to the problem. Going the extra mile, when multiple services are dependent on one service, it's also a good idea to mix an element of randomness. If a problem with one single service causes a large number of clients to fail at about the same time, then, even with backoff strategy, their retry schedules could be aligned closely enough that the retries request will hammer the troubled server. So, we can address this problem by adding some amount of randomness or jitter to each client wait time. This will space out requests across all clients and give the server some breathing room to recover. The timeout pattern is pretty straightforward to explain, but it might not be easy to get right. The goal of timeouts is to avoid unbounding waiting times for a response. When the time to respond is too high, the operation is aborted and the request is treated as failed. Timeouts are used in almost every application to avoid requests that get stuck forever. However, dealing with timeouts is not trivial. Imagine an order placement failed in an online shop. The buyer will see that the order wasn't processed, but in the backend, several things could have happened. We cannot be sure if the payment was successful, but the request response timeout on the way back, or if the request is still in progress in the payment system, or if the payment system was not even reached. All we know is that the request timed out. So, what status should we give to the customer? If we mark the request as failed, then the customer might think that the order didn't succeed, but maybe it did and he actually got charged. But since there was no response, the request was marked as failed. What happens if the customer retries the operation? In this case, he might get charged twice. Later, we'll see how to avoid double payments using the concept of idempotency. Now, we can retry the request ourselves in the backend using the strategies that we saw previously. However, again, we have to be careful not to charge the customer multiple times. Here, another question is how big should we set the timeout? This will depend on each particular endpoint. However, we should set them high enough to allow slower responses to arrive, but also low enough to stop waiting for a response that is never going to arrive. The fallback pattern enables a service to continue its execution even if requests to another depending service are failing. For example, while making a payment, a request might be sent to the fraud check service. But let's say that this service returns an internal server error. Instead of aborting the whole computation because of a missing response, we could fill in the fallback value. Otherwise, if the service is down, then no payment will go through. So, to avoid losing customers, we can fall back to a simple business rule. For example, if the amount is reasonably small, we can simply let the transactions go through. This is a compromise between risk and keeping the customers happy. Next, we'll see what we can do if the fallback value is not acceptable. Some failures can persist for a couple of minutes or even hours. What can we do in those cases? We can simply cancel the request if the failure is acceptable business-wise. However, there could be more to the story. In some systems, an error may persist because the information is not compatible between the sender and the receiver. In some cases, the error is not retriable because no matter how many times we resend the information, it will always fail. These incompatible messages are also called poison pill errors. So, to isolate the problematic messages, we can save them for later for debugging. For instance, we can save them in a dedicated queue so that we get rid of the broken messages. This pattern is also known as the dead letter queue. Later, these messages can be inspected to determine why they are not processed successfully. In other cases, an error may persist because one of the services is down, maybe for a couple of hours because of a serious problem. In that case, the error is retriable, so we may still want to accept the requests because we know we can process them later when the failed service recovers. Basically, we store in a persistent queue all the transactions that have failed and have to be consumed. Later, when the crashed service is up again, we can pick the transactions from the queue and process them. If a payment request fails due to a network error or any other reason, we should have a mechanism to safely retry the operation without charging the customer twice. To achieve this, we'll use the concept of idempotency. From an API perspective, an idempotent operation is one that has no additional effect if it's called more than once with the same input parameters. Let's see a usual scenario to understand how it actually works. Let's say that a customer makes a payment. The payment goes through our payment system and is successfully processed by the PSP. However, due to network errors, the response of the transaction fails to reach back to our payment system. The user will get back an error, so he will probably click again the pay button or retry the payment. Now, how can we avoid double payments at this point? We'll make use of an idempotent key. This is usually a unique value that is generated at the client and expires after a certain period of time. To perform an idempotent payment request, an idempotent key is added to the HTTP header in this form. UUIDs are commonly used as idempotency keys, and many tech companies are using it, including Stripe and PayPal. Usually, this UUID is also the ID of the payment order. Then, when the receiving server gets the same payment details, it will identify that it's a retry operation. To support idempotency, we can use the unique key constraint of any database. When the payment system receives a payment, it tries to insert a row into the database table. A successful insertion means we have not seen this payment request before. If the request fails, it means the key is a duplicate. So, the second request will not be processed. However, as the key already exists, we can return the latest status of the previous request. Moreover, if multiple concurrent requests are detected with the same idempotency key, only one request is processed and the others will receive 4 to 9 too many requests status code. In conclusion, an idempotency key is ensuring the exactly once guarantee. Lastly, if our payment system stores and serves a lot of data but is limited by a single machine, we need to graduate to a distributed system. Here, we can spin more database instances and also more payment services. Then, we can make use of the following benefits that it provides. Redundancy. This is achieved using replication. Usually, a distributed system can have multiple copies of data and processes. This will help us improve reliability by providing a backup in case one component fails. Then, in distributed systems, we can distribute the workload across multiple machines, which can improve reliability because we reduce the risk of a single component to be overwhelmed. Then, distributed systems can be designed to be tolerant of failures, allowing them to continue functioning even if one or more components fail. And last, we can easily scale up or down by adding or removing components, which again help us improve reliability by allowing the system to handle increased or decreased workloads. However, we should be aware that in a distributed system, the communication between any two nodes can fail, causing data inconsistency. Replication lag could cause inconsistent data between the primary database and the replicas. So, we should be aware of what consistency level we use when we read or write some data. One of the most effective ways to protect data is encryption. First, we should encrypt data at rest. This involves converting data into a secure format that cannot be read without a key. This can be done using software tools for disk encryption or database encryption. Then, we should encrypt data while it's being transmitted over a network such as the internet. This can be done at multiple levels. We can use a VPN. This will secure and encrypt connections between a device and the network. Then, at a higher level, we can use the TLS protocol. This provides confidentiality, data integrity, and authentication for the data transmitted between two parties, such as the client and the server. TLS should not be confused with SSL, which is deprecated since 2011. Then, at a higher level, we'll use HTTPS to transmit data. All these tools can be used to protect data that is transmitted over a network, but they each have different scopes and use cases. Then, we can implement access control. This involves restricting access to data only to authorized users and then using methods such as two-factor authentication to verify the identity of the users. Then, to avoid vulnerabilities, we should regularly update software, libraries, and the operating system. This involves keeping all software up to date with the latest security patches and updates. Then, we should backup data. If attackers manage to get or see the encrypted data, they can encrypt it again and then ask for a payment in exchange for the encryption key. However, if we regularly backup the data, we can ensure that it can be recovered in case of loss or damage. Finally, users should use uncommon passwords. For common passwords, like the word password, it's very easy for the attacker to guess the actual password if they have the encrypted version. They can use a rainbow table, which is basically a pre-computed table of reversed password hashes. Rainbow refers to the different colors used in the table to show the various hashing and reduction functions. So, a user should use long, complex passwords that are difficult to guess or to crack. Monitoring data integrity is a powerful security technique to secure business data against both known and unknown threats. In this process, we check if any changes have been made to vulnerable data. We assess the files of the databases and file systems and then generate a cryptographic checksum as a baseline. Then, regularly, We recalculate the checksum of the same resources, compare it to the baseline, and if we detect changes, we generate a security alert. This way, we can even detect malware within the operating system or other applications. However, this process can be very resource intensive, especially while dealing with large amounts of data. So, it's crucial to monitor data and files that are more vulnerable to cyber attacks so that you invest your resources efficiently. This data can be user credentials, privileges, and identities, or encryption key stores, operating system files, configuration files, and application files. For a payment system, reliability and fault tolerance are key requirements. To tackle these requirements, we discussed how to make use of the following tools, but not only: redundancy, to enable resilience during internal system failures; patterns for payment guarantee, by using Kafka capabilities to persist messages so that they are not lost even if the messaging system crashes; then, strategies for retry, timeouts, and fallbacks to make the system robust and predictable; then, messaging queues in order to avoid overloading the system; and idempotent message handling to allow clients to retry requests as needed. Not doing so could leave data in an inconsistent state or worse, in double payments.